Oh, unit 8, unit 8, unit 8, unit 8. I'm sure that's how you feel. Let's get it. All right. So we have one part where you're just finding the area between two curves. This part, which you're finding the area, I'm sorry, the volume of a solid that is generated when you rotate or when you revolve the area around an axis. And this part, it's just the x-axis. And then you have this one, which is supposed to be a little bit harder than this one, even though they're kind of the same. But you're revolving around x equals -3. Now, hopefully I gave you guys, or you have the updated copy. It doesn't say the x-axis right here. If it does, that's the same thing as this. So that doesn't matter, like this one. So you want to make sure that it says x equals -3. And then we have this really complicated one. College Board loves to throw these guys in there. So now I'm going to keep referencing, or I'm just going to be talking through these guys because these are the formulas that we're going to use. Actually, we're going to use this one, and we're going to use this one, the volume revolution. Actually, we're going to use the washer method too. But the washer method is just this guy twice. You see, it's outer minus axis, and then inner minus axis. So you get two volumes, and you have to subtract them. Okay, so let's start with the area bounded by these two curves. Now, we have a weird curve that's just a horizontal line, and then we have a regular kind of curve, which is x squared. It says find the area of R. So what we have to do is we have to go top minus bottom. And the reason why we're going top minus bottom is because if I just, if I look at the area between, let's see, our lower boundary and our upper boundary, they're first of all found by their points of intersection right here. If I found the area underneath this curve, it would be a rectangle. Actually, I don't know if it's a square, but anyways, it'd be a rectangle. It'd be this whole thing. But what we want to do is we want to take away this area that is underneath the parabola. So from here to here, from our lower boundary to our upper boundary, we want to take that area away from this whole thing so that we can find just the shaded area. So that's the top curve, the upper function minus the lower function. Our upper function is y equals 4. It's just a constant. It's 4. And our lower function is x squared. So first we find our points of intersection, and we do that just by setting these two dudes equal to each other. So I get x squared equals 4, and I get x equals plus or minus 2. Yay, there's my lower boundary, my upper boundary. All right, x1, x2. And then we have our upper curve minus lower curve, and then we have to integrate on this guy. So the antiderivative of 4 is 4x. The antiderivative of x squared is going to be x raised to the third power. Don't forget to divide it by that number now, or you can multiply it by 1/3. It looks like here I divided by 3 instead of multiplying by 1/3. Then you have to plug in the upper bound and then plug in the lower bound and subtract your two results. And so here I plugged in the upper bound, here I plugged in the lower bound, and then I subtracted them. But here you see a plus because what I did is I distributed the negative so I don't have to mess up my negatives because I always mess up my negatives. And then I get my answer. You don't have to simplify this anymore. Just leave it, all right? You're going to get it right. You don't have to simplify that. Okay, now to the fun stuff. A volume of a solid generated by revolving R about the x-axis. Now, our x-axis is y equals 0. That's our axis of revolution. So when you're looking at your formula right here, you have the outer minus the axis, okay? Now, this right here, it says the area of R, the region R. The region R is formed by two curves, so that means we're going to have to use the washer method. But before I talk about the washer method, let's just find the area, the volume of the solid formed with just revolving y equals 4 around this axis of revolution. Now, if I do that, I'm going to get these circles. Okay, if I get, let's get that back right here. If I revolve this around that axis of revolution, we get these circles. And these circles have a radius, and that's what I need to find the area of each disk or cross section. Okay, the area of a circle is pi r squared. In this case, to find r, I mean, it's just 4. The radius is just 4. But that's because our volume, our axis of revolution is y equals 0. So subtracting 4 minus 0 doesn't make sense to us because, going top curve minus bottom curve, because it's like, what, this 4 minus 0 is just 4. Okay, but if our volume or our volume was around y equals -1, then that would mean that our radius of our circle would be 5. Right, we would have to go 4 minus -1, which would give us 5. That would be our radius. Okay, so we don't have to subtract the axis of revolution for this problem because our axis of revolution is simply y equals 0. So to find this, this volume of the solid that's generated when I revolve this curve around the x-axis, I would have to take all the areas of each circle, and I would have to add them up. And I would be adding them from -2 to 2. Now this definition is just going to be 4, and we're going to square that. And then we're going to multiply it by pi to find the area of each circle. And then you have to add them all together from 0 to 2. And by integrating, you're doing that. Okay, now we could take out the pi right here because he's a scalar, and then we do our integration with the 4 squared, which is 16. But that's how you would find the volume of the solid that's formed with this curve. Now, the solid that's formed with this curve, it's going to look a little different. Okay, let me just draw it really quick. So we have this lower bound, this upper bound. When we revolve this guy around the curve, we're going to have this big circle, or I'm sorry, this small circle. If the curve, if it's this x value, it's going to be a bigger circle. So all the circles change their sizes based on which x value we're picking. Okay. Now, so what would the radius be of this circle? We can find out exactly by finding this x value and then plugging it into the x squared. Or we can just say x squared. X squared is going to be the radius of every single circle, depending on which x value you pick. You're going to square that radius, and you're going to multiply it by pi. Then you're going to add them all together from -2 to 2, and then that's going to be equal your volume. Now, we don't have to go curve minus the axis of revolution because the axis of revolution is just 0. Okay, that's what our formula says over here. It says outer minus axis of revolution. Okay, now this one has 2 r squareds. That's because this integral is combined. There's 2 integrals. There's the bigger volume, and then there's the smaller volume, and we just combine it, and we're allowed to because they have the same lower and upper bounds. And so that's what happens right here. Okay. Oh, look, I showed the axis right there, which is 0. So we have the volume of our top curve, and then we have the volume of our bottom curve. That's the volume of the solid that's formed when we revolve those. Here I combine the 2 because we have the same lower and upper bounds. Okay, so this is just 16, and this is going to be x to the 4th power. So I put that right here. I took the pi out of each of those, and now I just have to integrate that. So I do the antiderivative of 16, I get 16x. I do the antiderivative of x to the 4th, I get 1/5 x to the 5th. And then I have my upper bound and lower bound. I'm going to do all this stuff before I multiply out this pi. And so when I plug in the 2, I get this guy. When I plug in the -2, I get this guy. But I did change the signs because I didn't want to minus anymore. I wanted to add. And once I simplify this, I bring in the pi, and we're done. So there you have it. That's the volume of the region, or the solid when the region R is rotated around the x-axis. Okay, now the really, really complicated one, and that's this one right here. Okay, now, you know what? I'm just gonna make a different video for this guy because I want to do one for when we revolve around a vertical axis of revolution, and then I also want to do one when it's a horizontal axis of revolution. Okay, so look for my other video for that one. For this one, for D, it says there exists a number, k, and k is bigger than 4, such that when R is revolved around the line y equals k, the resulting solid has the same volume as the solid in part B. Okay, so it has this volume. All right. Write but do not solve an equation involving an integral expression that can be used to find the value of k. Okay, so I drew a horizontal line right here above this curve because this says that it's the volume of revolution is greater than 4. And so we're revolving around this axis of revolution, which means this is my outer curve now. Before, up here for B, this was my outer curve because we were revolving around this axis of revolution. Okay, so if I wanted to find the radius of this circle, I would have to go outer minus the axis of revolution. So it would be x squared minus k. That would be my radius of the greater volume. And then I would have to subtract from that because this is, we have two curves, so we have to use the washer method. 4 minus k, because that's going to be the radius of the smaller circles. Okay, so when I revolve just this curve around the axis of revolution, my radius is going to be the distance between k and 4. And so we just go the function minus the k, and that's going to give us our radius. Okay, so you have the outer function with your axis of revolution, the inner function minus your axis of revolution. That gives you your r and your r. You square those guys and multiply them by pi to get your areas. But then you have to add all those areas from -2 to 2 to find the volume, okay? So I just find, I write an expression giving me the volume that is formed after revolving this area right here around this axis of revolution. And then I set it equal to whatever my answer was up here. All right, now if this was a College Board problem, whatever your answer was right here, as long as you copy the same thing down here, even if this is wrong, this would be right because they're just looking for this part right here. Well, they're looking for this whole thing, but this is the main part that they're looking for.